Dear students, let's continue our practice on Mathematical Analysis 1. So the next topic is numerical sequences. Firstly, let's give a definition to sequence. What's sequence? Sequence, it's a row of the list or row or list of the number written in a specific order. For example, any row of the number. So 1, 3, 5, 10, 11, etc. So this is also sequence. Or, for example, -3, -1, and the next one is, for example, 0, 2, 5, etc. This is also sequence. You know, from school, some kind of types of the sequence, for example, arithmetic progression and geometric progression. There are also sequences. So, for example, 1, 2, 3, 4, 5, etc. This is arithmetic progression. Here we have difference 1, or we have geometric progression also. 1, 3, 9, and the next term it is 27, etc. Here the quotient is 3. So this is also sequence. So again, one more time, a sequence is a list of number written in a specific order. So here, if you want to write in generally, it is A1, for example, this is first term, A2, A3, etc., AN, and so on. It can be, we can continue here. So this is first term, A1. This is second term, we call third term, etc. Nth term of a sequence. So this is terms of a sequence. Sequence can be increasing or decreasing. If it is increasing or decreasing, we call it monotonic sequences. So here we have increasing sequence, and in this case also we have increasing sequence. If you want to write, for example, 1/2, then 1/3, 1/4, etc. This is now decreasing sequence because it goes to till 0 here. And AN, we call nth term of a sequence. And how to define here nth term of a sequence in this case? So here AN is 1 over what? Here we have 2, here we have 3, here we have 4, yeah? And if you want to begin from 1 here, if we add 1, what we get? This is 1/1, 1/2, 1/3, 1/4, etc. And we get AN, in this case, 1/n. This is general term of a sequence. So this is 1/n we get here. And now, consider the examples here. Example number 1. So, example number 1. Write down the first few terms of each of the following sequences. For example, n plus 1 over n squared, n equal 1 till infinity. So this one is means n here natural number. So this is number of the element in this sequence, number of the term n. So AN, we write in generally the sequences in this form: AN, n from 1 till plus infinity. So it means we have here a1, a2, a3, etc., an. Until infinity it is. So this is general form of a sequence. Now, or we can write just an. Similarly, we can write a1, a2, an. This is given form of a sequence. Now, so we have this sequence. Let's write first few terms of this sequence. How to write? It means we should write a1 firstly. a1 is, instead of n, we have to put 1 here. So we get 1 plus 1 over 1 squared. So what is it? It's equal to 2 over 1. So it is 2. Now, the next one, a2 here. a2 is, similarly, we need to put here 2 instead of n. So 2 plus 1 over 2 squared. So it is 3 over 4. And the next one, for example, we can write a tens, for example. So it is, instead of n, we need to put 10. 10 plus 1 over 10 squared. So the answer is 11 over 100. And so on. We can continue. So this is a few terms of this sequence. And now, so let's consider the next example. So the next example is this one, number B. So minus 1 the power of n plus 1 over 2n's power. So n from 1 till infinity. So here, how to define? Again, so a1, let's define a1. So it means instead of n, we should put 1. So here what we get in this case, it is minus 1 the power of 1 plus 1. So look here, n is always natural number. This is number. This is number of a sequence, a term. So minus 1 the power of 1 plus 1 over 2 the power of 1. So here we have minus 1 the power of 2. It is 1 positive over 2. And the next one, a2. a2 is, so minus 1 the power of 2 plus 1 now over 2 the power of 2. So here what we get? We get minus 1 the power of 3. It is negative 1 over 2 squared. So it is 4. Minus 1 over 4. So this is how to write down the few terms of a sequence. If we have general term of a sequence. So this is general term of sequence. Now, let's continue. So, here, and now, you can give a definition to a limit of this sequence. Firstly, what is limit of the sequence? So, we have two types of definition. Working definition. The first one is, so what is the working definition? We say that if a limit of an sequence an is L when n goes to infinity, if we can make an as close to L as we want for a sufficiently large n. So, in other words, the value of an's approach L as n approaches infinity. So, for example, let's consider one example. Here, what we have? Here we have limit n tends to infinity an. So an is n plus 1 over n squared. So n plus 1 over n squared. So let's find the limit of this sequence, of this numerical sequence, n plus 1 over n squared. So look here, this is which one goes to infinity faster. In this case, the numerator is less than denominator, because here we have power n squared, 2 times n it means. So it means denominator is greater than numerator and it goes to 0. If denominator goes to infinity faster than numerator, such kind of sequence goes to 0. So now, and what kind of sequence it's increasing or decreasing? This sequence is look here, let's find terms of this sequence. Firstly, let a1 write. a1 is 1 plus 1, 2 over 1, it is 2. Now a2, it is 2 plus 1 over 2 squared, it is 3 over 4. The next one, a3, it is 3 plus 1, 4, 4 over 9. We can prove it. So, and the a4s, for example, it is 4 plus 1, 5 over 16, etc. Yeah? So here we have what kind of sequence we get? 2. The next term is 3 fourths. The next term is 4 ninths, 5 sixteenths, etc. So this sequence is decreasing because the terms, when n increasing, the terms are decreasing. So this is decreasing sequence, an decreasing. So now it goes to 0 because the numerator goes to infinity and it's bigger than denominator. I mean, denominator goes to infinity and it's bigger than numerator. So in this case, we can say it goes to 0. Now let's give let's continue. So here we have the next definition with epsilon and this epsilon. So here, let me clear. So the next definition is, we say that limit n tends to infinity an is equals to L if for every number epsilon greater than 0 there exists such kind of n. This symbol is exist. n, capital N, such that for all, we denote for all by this symbol, for all n bigger than n, it satisfies absolute value of an minus L less than epsilon. This is general definition of a limit of a sequence. So this is definition. And now, when we go to the examples, I will show how to find the limit with definition and without definition also. So, now let's move to the examples. So here we have some properties of limit sequences. So let an and bn be two sequences such that limit an is equal to n and limit bn is equal to b with a and b real numbers. Then the following results hold. So the first one is the sum of the limit. It is the limit of sum. It is sum of limits. So limit an plus bn, it is limit an plus limit bn. And multiplication is same. So, and we have other ones, and we will do it during the solving the practice examples. So, we have examples here. Okay, so problem number 1. Write down a few terms of the below sequence given by their general terms. So here we have general terms, and we can write the few terms of these sequences. So let's do some kind of more difficult of them. So number 4, for example. So here an, let's write one more time. It is minus 1 the power of n plus 1, 3 the power of n over 2n minus 1 factorial. So how to write now a1 here? A1 it means instead of n we should put 1. So a1 is minus 1 the power of 1 plus 1, 3 the power of 1 over, where n we put 1 just. So 2 times 1 minus 1 factorial. So here we have minus 1 the power of 2, it is 1, positive 1. 3, the first power, it is 3. And 2 minus 1, it is 1. 1 factorial, it is 1. So the answer is 3. So this is first term. Now, next term, a2 is here again, minus 1, the power of 1, 2 plus 1, 3, the power of 2, and over 2 times 2 minus 1 factorial. So it is equals to, now what we get here. So minus 1 the power of third, it is negative 1, times 3 squared, it is 9, over 2 times 2, it is 4, 4 minus 1, it is 3, 3 factorial. So, and now minus 9 over 3 factorial. It is 1 times 2 times 3. It is 6. We can cancel them and we get the answer if we cancel them by 3, and we have minus 3 over 2. So this is second term of this sequence. Now we can continue, find third terms, fourth, fifth, etc. I think it's clear. Here let's define the first term, a1. What is it? A1 is cosine pi over 2, because instead of n we need to put 1. A2, it is cosine pi times 2 over 2. We can cancel them and we have just cosine pi. And the a third, so it is cosine pi times 3 over 2. And we can get the numerical values of this function, cosine. Okay, now problem number 2. Find the general terms of the below sequence given by a few first terms. So now we need to do inverse operation. Find general term by this from these terms. Okay, let's continue. Let's given the following sequence. We need to find from these first few terms the general term of a sequence with n. So here, what kind of general terms we can get? Let's consider 1 over 2. So 1 over 5, 10, 17. Here, if we can write, so in this case we have 1. If you write in generally, it is n squared plus 1. Is it correct or not? Let's check it. N squared plus, why n squared plus 1? Because it is 1 plus 1, 1 squared plus 1. I mean, it is 2 squared plus 1, it is 3 squared plus 1, it is 4 squared plus 1, etc. So we have 1 over n squared plus 1. If you put 1, we get 1 over 2. If you put 2, we get 1 over 5. If you put 3, we get 1 over 10, 1 over 17. If you put, for example, 5, we get 1 over 5 squared plus 1. So it is 26, and etc. So this is general term of the following sequence. Now, by this way, we can define the other ones also. For example, number 6 here. It was number 1. Number 6 now. So, 1 over 2, 2 squared over 2 squared. So 3 squared over, I think 2 cubed, yeah, 2 cubed, and 4 squared over 2 fourth degree. So you need to find the general term of this sequence. Here, firstly, find a rule of this sequence. What kind of rule we have here? So look here, the first one is 1 over 2, the second one is 2 squared over 2 squared. So if we consider numerators, just only numerators, 1, 2 squared, 3 squared, 4 squared, etc. Next one is 5 squared, 6 squared, etc. So here we can write 1 squared instead of 1. So it means in numerator we have n squared. And now, denominator, what we have in the denominator? 2, 2 squared, 2 cubed, 2 fourth degree, etc. This one is 2 first degree. So it means 2 nth degree we have. This is general term of our sequence. N squared over 2n. So now, this is how to write from given few first terms, general terms of a sequence. Okay, now the next example. So using definition, prove that limit n tends to infinity, an is a if. Now we need to use a definition. Let's one more time remember definition. So for any epsilon greater than 0, there exists a number n, capital N, such that for all n greater than n, this number satisfies the following inequality: absolute value an minus a, it's less than epsilon. So this is, and we get this limit. So this is general definition of a limit of the sequence. And now let's use this definition and prove that they are equal. For example, number 1, an is 2n minus 2 over 3n minus 1, and a is 2 over 7. So 2 over 3 here. Let's use this definition. For any epsilon greater than 0, there exists number such that for all n is greater than n, big capital N, we get. So instead of an, now we put this one. This is instead of an. So 2n minus 2 over 3n minus 1. Now this is, and minus a. Our a is 2/3. It is. Now let's continue this difference. So what we have here, if you doing common denominators, so here 3, here 3n minus 1, and we get 6n minus 6 minus 6n plus 2 over 3 times 3n minus 1. And now if we continue it, so equals to, they are cancelled, 6n and 6n. We have minus 4 over 3 times 3n minus 1. So this is less than epsilon. So we can write here just 4, because this is absolute value, over 3 times 3n minus 1 less than epsilon. Now we need to find this number, and there exists such kind of n capital. So if we continue here, we can find n with epsilon. So, and it will be our capital N. So let's find n. Multiply to the right side and divide by epsilon. So 9n minus 3, it is greater than it is greater than, because it goes to the right side. So 9n minus 3 is greater than 4 over epsilon. Let's find n now. 9n greater than 4 over epsilon plus 3, or 9 is greater than, let's divide by n is greater than, let's divide by 9, so it is 4 over 9 epsilon plus 1 over 3. And now you can write our capital N as, let's write here, and now N is, this is 4 over 9 epsilon plus 1 over 3. And to write our N, because here it is, N is greater than N. So it is 4 over 9 epsilon plus 1 over 3 plus 1, integer part of this number plus 1. This is our n. So we found our n. It means we proved that an, limit of an is equal to a. This is proving using the definition. Now let's continue. So problem number 5, calculate the limits now. Now let's calculate how to calculate the limits. So first one, limit n tends to infinity, 2n squared plus 3n minus 1 over 12n squared minus 7n minus 8. So here we need to find the limit without using a definition. So how to find it? Look here. Here we have n squared, the biggest power in numerator, and in the denominator also n squared. So in all cases we need to divide by the greatest term in our expression. So in this case we need to divide by n squared, numerator and denominator. How? So it's very easy. Limit n tends to infinity, 2n squared over n squared by terms, by each terms, plus 3n over n squared minus 1 over n squared over, now 12 n squared over n squared minus 7n over n squared minus 8 over n squared. So here what we have, if we continue, limit n tends to infinity, here we have 2 plus 3 over n minus 1 over n squared over 12 minus 7 over n plus minus, it was minus 8 over n squared. So now remember, n tends to infinity. It means it is 3 over infinity. If we have a form 1 over infinity, it goes to 0 because the denominator goes to infinity and our expression goes to 0. And if we have expression 1 over 0, it goes to infinity. If our denominator goes to 0, it will be inversely, so it goes to infinity now. Let's use this property. So here we have 3 over infinity and minus 1 over infinity. It means it goes to 0 and it goes to 0 also. And this one goes to 0 also, and it goes to 0 also. So what we have? We have just 2 over 12. This is answer. Or just we can cancel them, 1 over 6. So this is our limit, 1 over 6. And one more thing here. If we have in denominator and in numerator the greatest powers are equal, the greatest powers are equals, it means the limit such kind of fractions or such kind of expressions equals to the ratio of coefficient of greatest powers. I mean here the ratio of greatest powers, coefficient of greatest powers, it is 2 and 12. So the answer we can write directly 2 over 12 or 1 over 6 here. Because look here, when we divide them by each terms, we get this answer, 2 over 12. So now let's consider the next example. So here the second one, limit n tends to infinity. So 3n squared plus 7n plus 8 over 2n cubed plus n minus 2. So what we have here, the greatest powers are different in numerator and in denominator. Here n squared, here n cubed. Again, let's divide to the greatest power of n, numerator and denominator, and we get n tends to infinity, 3n squared over n cubed. In this case it is n cubed, the greatest power. 7n over n cubed plus 8 over n cubed over 2n cubed over n cubed plus n over n cubed and minus 2 over n cubed. If we continue, what we have here, it is 1 over n, 3 over n, we have coefficient also, it doesn't matter in this case. So this one is 7 over n squared plus 8 over n cubed over. So the denominator is 2n cubed over n cubed, it is 2, plus 1 over n squared and minus 2 over n cubed. Similarly, from previous example, they goes to 0. And we have just 0 plus 0 plus 0, 0 over 2. The answer is 0. Conclusion. So if we have here, if the power of denominator, the n's power, denominator is greater than the power of numerator, in this case we get 0. If, one more time, if the power of n of the denominator is greater than power of n of the numerator, it goes to 0. Otherwise, if the power of n of the numerator is greater than the power of the n of the denominator, it goes to infinity. For example, if we have limit n tends to infinity, 3n cubed minus 1 over 2n squared plus n. For example, it goes to infinity because here the power of here n cubed, the power of numerator, power of n of the numerator is greater than n cubed here we have, and we have here in the denominator here we have n squared. That's why it goes to infinity, because numerator is greater than denominator and goes to faster to infinity than denominator. Okay, now the next example. So the next one is number 3. Limit n tends to infinity 12 over n plus 2 minus 1 over n squared plus 4. So what should we do here? In this case, we need to simplify firstly expression inside of these brackets. So limit n tends to infinity. Let's do in common denominator. So 12 n squared plus 48 minus n minus 2 over, let's multiply them, n cubed plus 4n plus 2n squared plus 8. So now let's simplify. What we get? 12n squared minus n plus 46. And now in the denominator we have n cubed plus 2n squared plus 4n plus 8. So here the power of denominator, the power of n from the denominator, it's greater than power of n of the numerator. So the answer is just 0. You can continue it by dividing n cubed and you get 0 again. So now the next example. And if we want to find separately, not always we got the correct answer. That's why firstly we need to simplify them. Okay, so the next example is number 4. Limit n tends to infinity 2 n plus 1 plus 3 n plus 1 over 2 the power of n plus 3 the power of n. Okay, now how to find here. Let's open this 2n plus 1 and 3n plus 1. It is 2, don't miss the limit, 2 times 2 to the power of n plus 3 times 3 to the power of n over 2 to the power of n plus 3 to the power of n. If we continue, here now we can divide by one of them, 2 to the power of n or 3 to the power of n. Let's divide by 3 to the power of n. And we get 2 limit n tends to infinity. So 2 times 2 to the power of n over 3 to the power of n plus 3 times 3 to the power of n over 3 to the power of n over 2 to the power of n over 3 to the power of n plus 3 to the power of n over 3 to the power of n. Okay, now what we have here? Look here. It is 2 limit n tends to infinity 2 times 2 third the power of n. Yeah? Plus 3. Because they are cancelled. 3n and 3n. n is natural number. So, next one. It's also 2 over 3 n's power plus 1. Let's continue. Here, 2 over 3, let's consider to limit n tends to infinity 2 over 3 power of n. Is it greater than 1 or less than 1? This is less than 1. And however this is less than 1, it goes to 0. Because it is less than 1 and goes, for example, if you want to write the by terms, it is 2 over third, the first one. The second one is 4 over 9 instead of n2. The next one is 8 over 27, etc. Look here, it goes to 0. So they are goes to 0. And we have just 2 times now we can we cannot write a limit, so 2 times 0 plus 3 over 0 plus 1. The answer is 3. So this is number 4, and we get the limit is 3. Okay, next one. So, number 5. Limit n tends to infinity n squared plus 2n minus n squared minus 3n over 5. So, if we have square roots, we have a formula, short multiplication formula. You remember a squared minus b squared. It is a minus b, a plus b. So we need to use this formula now. And how to use? Multiply by conjugation of this expression with plus and divide by it. So if we continue, here we have limit n tends to infinity, multiply by conjugation with plus and divide by them. So n squared plus 2n minus n squared minus 3n times n squared plus 2n plus n squared minus 3n. This is formula. Okay, so and divide by 5 times this one, this plus, yeah? So n squared plus 2n plus n squared minus 3n. So now let's continue. If we continue our fraction, we have limit n tends to infinity. So if you multiply them, we get n squared plus 2n minus n squared plus 3n, because here we have double minus. Without square roots now we have, because a squared minus b squared. So 5 n squared plus 2n plus n squared minus 3n. Now let's continue. You can cancel n squared with n squared, and we get 5n here, and we can cancel 5 by 5. We have n limit n tends to infinity n over this expression now. So now how to define, how to continue? N over square root here, sum of square roots. So now we can divide by n, because this is square root, and if we take out from this square root, we get here n, because it's n squared. N squared from square root, it is n. So it means the greatest power of n is just first power. Let's divide by n first power. So 1 over here, because n over n, divide by 1 divide by n. So n squared over, now when we do it in square root, we have n squared instead of n, because we divide by n, but in this case we have square root here. In the inside of square root it will be n squared. So square root of 1 plus 2n over n squared plus same 1 minus 3n over n squared. So they are goes to 0, these two ones, and it is goes to 0 also. And what we have? Square root of 1, square root of 1. So it is 1 plus 1, 2. 1 over 2 we have half. This is answer. Half. So it was number 5. And now let's continue. So number 6 now. Limit n tends to infinity. The sum 2 over n squared plus 6 over n squared plus etc. The general term is 4n plus 2 over n squared. And now let's continue. In the denominator we have n squared. They have common denominators. So in numerator we have 2 plus 6 plus 4n plus 2. So and now how to find this sum? 2 numerator 2 plus 6 plus etc. plus 4 and plus 2. The next, let's write here 2 plus 6. The next one is here. When we put 2, it is 10. I mean here plus. The next one is, if you put 3, it is 12 plus 2. It is 14, etc. So we have this one. How many terms we have here? We have n terms. So now find the sum of this sequence, this arithmetic progression. So it is, let's denote by Sn or Sn. It is a1 plus an over 2 times n. By this formula should find. So here we have a1 is 2 plus, first and last one, 2 plus 4n plus 2 over 2 times n. So the answer is 2 plus 2, it is 4. So we can take out the 4. 4n plus 1 over 2 times n. Can cancel them, it is 2. So the answer is n squared plus n times 2. 2n squared plus 2n. And now we can continue here. It's equals to this one now. Yeah, this is we put here. So, and now if we continue, it is limit n tends to infinity. Now 2n squared plus 2n over n squared. So what we get here, if we divide by the greatest term, it is n squared. It will be 2 over n squared over n squared. It is 2 times n squared over n squared. It is 2, like this. And we have here the answer. So it is 2 over n and 1. So when n tends to infinity, it tends to 0, and the answer is just 2. This is answer. So it's answer of the problem number 6. By this way we can continue the other ones, number 7 and number 8. Try do these ones at home, and we have the next exercise also. So these ones, number 9, number 10, number 11, number 12, and problem number 6. Find again limit. So try to find these limits, and the next time we'll continue the topic numerical sequences, especially limit of the numerical sequences, and we will do other ones. Goodbye.